Hello everyone. I welcome you to the class of econometric methods. Myself, Dr. Imdadul Haq, is an associate professor at the Department of Economics in Aligarh Muslim University. Today we would be focusing on the significance of the error term. The theory governing the behavior of the dependent variable y, if it exists, is frequently incomplete. While we may have a definite knowledge that, say, weekly income or monthly income has an impact on monthly consumption expenditure y, there may be uncertainty or a lack of information regarding other variables which are influencing the dependent variable y. Consequently, the error term can be employed as a stand-in all for all the variables which are excluded or omitted from the model. The first case we will discuss is the unavailability of data. See, even if we are aware of some of the excluded variables and opt for multiple regression instead of a simple regression, we may lack quantitative data on these variables. Empirical analysis often involves the challenge that the desired data may not be accessible. For instance, while it could be theoretically beneficial to include, say, family wealth as an explanatory variable alongside income to elucidate family consumption expenditure, but the information on family wealth is typically unavailable. So consequently, we might be compelled to exclude the wealth variable from the model, despite its significant theoretical relevance in explaining the consumption expenditure. And the core variables versus the peripheral variables. In our example of consumption and income, let us assume that in addition to income, factors such as number of children per family, gender, religion, education level, geographical region also impact this consumption expenditure. However, it is plausible that the collective influence of these variables either entirely or, say, partially is minimal and lacks systematic patterns. From a practical standpoint and considering cost considerations, it may not be worthwhile to explicitly incorporate them into the model. The expectation is that their cumulative impact can be regarded as a random variable which we denote by u. Then comes this intrinsic randomness in human behavior. Say, even if you manage to incorporate all the variables into the model, there will inevitably be some inherent randomness in individual outcomes that is yet to be explained, regardless of the efforts. The disturbance represented by the variables, the error term variable u, may indeed capture this intrinsic randomness. The next factor would be this proxy variable, a poor proxy variable rather. While the classical regression model assumes precise measurements of variables y and x, the dependent and the independent variable, but real world data may be susceptible to measurement errors. Take an example of this Milton Friedman's renowned theory of consumption function, the permanent consumption theory, where he links permanent consumption to permanent income. But in practice, since direct observation of these variables is not feasible, so proxy variables, like for permanent consumption, we are taking a proxy variable of current consumption, and for permanent income, we are taking a proxy as current income. So these proxy variables like current consumption and current income are implied. But as observed, this dependent and independent variable, the proxy one, may not precisely correspond to permanent consumption and permanent income. So in that case, this measurement error is a thing of concern. In such cases, the disturbance term may also signify the measurement error. If these measurement error exist, they can significantly impact the estimation of your beta 1 and beta 0, that is the regression coefficient. Then we come to the principle of parsimony. See, adhering to Occam's razor principle, we aim to maintain simplicity in our regression model. The simpler, the better. So, if we can adequately account for the behavior of y with say 2 or 3 explanatory variables, and our theory is lacks a robust suggestion for additional variables, there may be no need to introduce many more variables. In this context, let the error term, that is your u, it represent all the other variables. However, it is crucial to exercise caution and not exclude pertinent variables that are relevant and important merely for the sake of simplifying the regression model. Now, the next one, it could be the case of a wrong functional form. Say we are taking a functional form that is a linear one, but it may be that in reality we need another term of x square, we need a non-linear term to be incorporated in the model. Say, even if we have theoretically sound variables to obtain a phenomenon and can obtain the data on these variables, the challenge often lies in not knowing the precise form of this functional relationship between the dependent and these independent variables. For example, say in the case of consumption expenditure only, we may be uncertain whether it follows a linear function or there is a non-linear relationship. If it is the former one, the linear one, that is yi is equal to alpha plus beta xi plus ui, it represents appropriate function relationship between I and x. But if it is the later one, that is yi is equal to alpha plus beta x1 plus gamma x square plus ui, then if this may be the correct functional form, but in the two variable model, the relationship form can often be expressed through the scattered diagram. Determining the suitable form becomes challenging in multiple regression models where scattered diagrams in multiple dimensions cannot be visualized graphically. So we have, it could be this error term could capture your the things which are there in the wrong functional form. With this brief discussion on the importance or the significance of the error term, we now move on to the assumptions of ordinary least squares method, or you can say the assumptions of the classical linear regression model. Most of these assumptions are related to the same error term whose significance we have just now completed as such. The first, suppose we take this regression equation as y is equal to alpha plus beta x plus u. Now herein this ui is basically the random variable or the error term. The value which ui may assume in any one period, it depends purely on chance. It may be positive, it may be negative, it may be zero. But each value has a certain probability of being assumed by ui in a particular instance. So the very first assumption which we have over here is that ui is a random variable. The second assumption is the expected value of ui is equal to 0. See, this ui, the error term, is a random variable. That is, it takes values by chance and it doesn't change in a systematic way. Therefore, we say that expected value of ui is equal to 0, which means the positive values of the error term will cancel the negative values of the error term. Then we have the next assumption again with the error term is that it is constant. The variance of the error term, the variance is constant. Like if you see the two diagrams which are given over there, the first one, it has, obviously there is a regression line, it is regressed on a lot of, and the scatter points are there. There is an error term, all the points are not lying on the error term. So what happens is that but almost the error term is constant. The amount of error which is there in the very start is the same amount of error is there towards the end. But in the second diagram, you can see in the initial time period, the amount of error is small. The spread of the error around the regression line is small as compared to when towards the end you find that the regression is that error term is huge. So this one is an example which we assume that if this is the case, then our estimates will be problematic. So we assume that our the expected value of ui is constant. The variance is constant at a given value of x. So there are several values of y. It means that if the variance of ui is associated with xi and yi is constant and same as the variance of ui associated with say x1, x2, x3 and likewise. The variance of ui about its mean is constant at all values of x. Or we can also say that for all values of xi, the ui's will show the same dispersion around the mean. If this assumption is violated, we will see that it is the case of a heteroscedasticity. We will see that in our later classes. Then another assumption is the variable ui, it has a normal distribution. So, if this is again an assumption, the values of ui for each of these x1, x2, x3, x4 have a bell-shaped symmetrical distribution about their zero mean. So we had four assumptions. We have seen four assumptions. The first one, it's a random, ui is random, the mean value is 0, the variance is constant, and the error term has a normal distribution. All these, it can be, these four is normally you will constant variance. The above four assumptions about the behavioral distribution of the mean values is summarized by this expression given below. Now, we come to the next assumption. This assumption says that two values of the error term, they are not related, or in symbolically, it is expected value of ui, uj is equal to 0. This means that all the covariances of any ui with any other uj, one error term at one period ui denoted, the next period is uj, are equal to 0. The value which the random term assumed in one period does not depend on the value which is assumed in any one other period. Like see, we have a case over here. These are, in this case, a positive value. Anything above this line is positive and this anything beneath this line is negative. So this is what happens in this case. The positive values are, the positive error terms are associated with positive error terms. Positive values are associated with positive values, and again negative values is followed by negative values. Then again positive values is followed by positive values are followed by positive values of the error term. So there is a systematic pattern. This assumption is violated. We come again to the second one. It says it's alternating, a positive and a negative, next time positive, negative, positive, negative. Above this line is positive, beneath this line is negative. So there is positive, negative, positive, negative. A pattern follows. Again, this is again a case where your assumption that expected value of ui, uj is not equal to 0. So if this assumption is violated, we go into the realm of serial correlation. If this assumption is violated, we will see in our later chapters, in our later discussions, that this is the problem of serial correlation. Then, the relationship between the independent variable and the error term, it should also be 0. The expected value of xi, ui, that is the error associated with xi, it should be equal to 0. This basically implies that there is no correlation between xi and ui. There is as such no correlation between these things. This assumption is automatically accepted because say xi has a set of given systematic values and ui is a random variable. So the disturbance term here is not correlated with the explanatory variables. As such, you can also say that the u's and the x's, they do not tend to vary together, or you can say that the covariance between these two is equal to 0. So this is again one of the assumptions. This also we can relate with this assumption that the xi's remain same in repeated sampling. If we recall this this discussion that we have the data of monthly income and we have taken certain exact level of incomes like 90, we have taken a family whose income is 90, whose income is 100, whose income is 110, whose income is 120, whose income is 30. Now, for a family whose income is 90, there may be many families whose income is now 90. Now, one of those families' monthly consumption expenditure is 50, the next family's monthly consumption expenditure is 55, 60, 65, 72, 76. But this X is fixed. Again, we take another family income level of say 100. Now, this is associated with one family which is having a different consumption level, consumption expenditure level 60, than the another consumption expenditure level of the other family whose monthly income is 100 is 65. So likewise we have different families. So when we are going for several samples, the values of the independent variables, that 90, 100, 110, 120, 120, 130 will remain the same. Now again, as we have discussed just before, that with relation to the measurement and its error. So we assume that this explanatory variable are measured without any error, and u, that is the error term, it absorbs the influence of the omitted variables and the possible errors in measurement of y's. That is, we will assume that the regressors are error free. So while the y values may or may not include the errors of measurement, but we assume that they are free. Next one is that the explanatory variables are not perfectly correlated. Now this again, if we go to the realm of multiple regression. Now in multiple regression there is not more than one independent variable. If it is only one independent variable, so that comes to the simple regression, and if we have more than one, then we have multiple regression type of thing. Now in this case, if say if it is y is equal to alpha plus beta 1 x1 plus beta 2 x2, so we assume that this the variables or the values of x1 is not having any relationship with it's perfectly related with the values of x2. So if there is more than one explanatory variable in the relationship, it is assumed that they are not perfectly correlated with each other. Indeed, the regressors should not even be strongly correlated. If it is, then they are multi-collinear, and in that case we again have a serious issue which is called as multi-collinearity. Now the next assumption is that these macro variables, again, they should be correctly aggregated, in the sense that usually the variables x and y are aggregate variables of individual items. For example, in the consumption function, say c is equal to alpha plus beta y plus u. C is the expenditure of the consumers and y is the sum of the individual incomes. It is assumed that the appropriate aggregation procedure has been adopted in compiling the aggregate variables. Now, the next one is the relationship being estimated is identified. Again, this is assumption. So it is assumed that the relationship whose coefficient we want to estimate has a unique mathematical form. That is, it does not contain the same variables. The same variables or any other as any other equation related to it being on one being estimated. Only if this assumption is fulfilled can we be certain that the coefficients which are result from our computations are the true parameters of the relationship which we are going to study. This will lead to the simultaneity bias and the identification issues. So we assume that this relationship being estimated is properly identified. The last one would be, we can say that we assume that the relationship is correctly specified. So it is assumed that we have not committed any specification error in determining the explanatory variables, that we have included that such we have included all the important regressors explicitly in the model, and that its mathematical form is also correct. So the relationship has been correctly specified. This is also one of the assumptions of this classical linear regression model. So if we quickly go through the assumptions, most of the assumptions, they are related to the error term. Error term is random variable, expected value is 0, the variance is constant, and the error has a normal distribution. Then the next one was also, that is, two error terms are not correlated with each other. The error term is not correlated with the independent variable. So up till here we had these 6 assumptions, 4 and then 4 over here, and then the 5th one and the 6th one. These 6 assumptions are related to the error term. Then we have this again regarding the values of x, they are fixed, and these explanatory variables are measured without error. There is again the two explanatory variables are not related, properly aggregated, properly identified, and properly specified. All these are the assumptions which we have over here. Now subsequently we will be seeing in our coming lectures that what happens if the assumption is violated, like if the error term is not constant, the variance of the error term is not constant, then we have a problem. Then what is the problem and what is the solution to the problem? Again, if two error terms are correlated, then what happens to the estimate? Can we take, is our sample estimate a proper estimator of the population estimates? So likewise, when then we will relax. So we will see that what is the solution to it. So likewise, in subsequent chapters, we will be relaxing the assumptions and looking over here. But this error term is a very important component. This error terms makes it a stochastic, and this is the beauty of regression. So we consider the error term, we are considering the relationship, but in a world we cannot perfectly specify, there is nothing like exact relationship we can say. So we have the errors. If the errors are satisfying the conditions, only then the estimates of the regression can be used for estimating the parameters properly. Thank you.